Okay, so let's finish up with our covalent bonding, and this time we're going to start talking about intermolecular forces. So remember that these are the bonds between molecules, and they help us work out what the melting point or boiling point of a substance would be. So just reviewing that, okay, we're talking about these dashed lines here. These are our intermolecular attractions. Okay, so these are the attractions between molecules. Okay, remembering that molecules are discrete entities, so they're individual things of their own, and how strongly each individual molecule is attached to each other, or attracted to each other rather than being attached, is what we're talking about here. The intramolecular bonds are the ones that we represent between the two atoms here. Okay, so this is our intra. And intramolecular bonds are always between two atoms, okay, whereas intermolecular bonds are between whole molecules. And the intra can be polar or nonpolar. Inter, we have a completely different naming system entirely. Okay, so the intermolecular forces are what determine the melting and boiling point of substances. So if you remember the properties of our covalent molecules, okay, and covalent substances, they tend to be waxy, they're gases and liquids at room temperature, okay, so they tend to have much weaker forces, is what that's telling us. Okay, but this time when we talk about the electrostatic attraction, and of course it's always electrostatic attraction with our bonding, when we talk about the strength of electrostatic attraction, this time it's between molecules. Okay, so whether or not a molecule is polar or nonpolar and its size is what's going to make all the difference to the strength of these forces. Okay, let's look at water. Water is a really great molecule for us to look at with intermolecular bonding because its special intermolecular bonding gives rise to all its amazing properties that make it so useful. Okay, so in an individual water molecule, we have polar bonds, okay? Whoops. Okay, so we have polar intramolecular, okay, so covalent bonds, polar covalent bonds. Okay, in that case. And then with the delta positive being where our hydrogens are and the delta negative up where our oxygen is, because the oxygen will be the more electronegative. Okay, so water is held together by these intermolecular bonds between water molecules. Okay, so this means that when it changes state, so when we're going from a solid to a liquid or a liquid to a gas, it is these bonds, the intermolecular bonds, okay, that are broken in a phase change. Okay, the water molecules will still be water molecules, there'll just be more space between them, so there's less intermolecular bonding. Okay, we're not breaking apart, we're not ripping a hydrogen off, okay, when we boil it. What we're doing is just increasing the space between these molecules here by breaking these ones. Okay, so we need to look at our intramolecular bonds and consider whether what they're doing. So these are the covalent bonds within the molecule, so they will be polar or nonpolar. And then we look at the intermolecular bonds, which are the ones that are between molecules. There are three main types of intermolecular bond that we will talk about, and you need to be able to identify these in substances as well as talk about their relative strengths. Okay, basically these are much weaker than covalent metallic or ionic bonds. Okay, so they're holding the substance together, but they're not bonding the atoms together. And they determine the state. Okay, if the intermolecular force is strong, then the boiling point or a melting point of a molecular compound is high. Not high compared to ionic or metallic, but say water where it's 100 degrees. So we're not talking thousands of degrees in this case. What we're talking about is high relative to, say, methane, which is a gas. So, okay, the first that we need to look at is London forces, which are the weakest of our forces, dipole-dipole interactions, and hydrogen bonds. Okay, so the London forces are our weakest. These are referred to as dispersion forces. Okay, so you can hear them being referred to as these in different examples. Okay, so this is our weakest. So we're going from weakest to strongest, and these are our three different types. So van der Waals forces is a term that is used in the IB, okay, and it is one that refers to London forces and dipole forces together. Okay, so these ones together are van der Waals. Okay, in old test papers, they used to say that van der Waals forces were equal to dispersion forces. This has changed. Okay, so if you're going through old questions, you need to remember now that these are now van der Waals forces, London forces, and dipole forces. Questions on this do come up, and you do need to know the difference between them. Okay, so in non-polar molecules, okay, there's no permanent dipoles. Okay, so if we have Cl2, remember there's no electronegativity difference, so it's non-polar. Okay, in polar molecules such as water, we know that we will have a delta minus and a delta plus, and we will have an overall dipole, so water will be a polar molecule. Okay, so if they're non-polar, okay, they tend to be quite, most of them tend to be gases, things like methane and otherwise, okay? But we do know some of these are liquids or solids at room temperature. Examples of this are oil, fats, waxes, okay? So what this can tell us is that as we increase the size, we increase the intermolecular forces. Those forces are getting stronger. Okay, so what we also know is that there has to be some form of attraction in non-polar molecules, because if it was all like methane, okay, then they would just all be gases at room temperature. But as they get bigger, so say we've got something like 1, 2, 3, 4, 5, 6, 7, 8 octane, okay, this would be a liquid at room temperature. So we know that there has to be some kind of attraction with these, okay? So if there is, okay, if there wasn't, they would all be gases, okay? But there's not. These non-polar molecules have what we call an instantaneous or temporary dipole moment. If you think back to atomic structure, we said that we had the central nucleus of our atom, and then we have the electrons circling around it in shells, and we said with the quantum model that was sort of more like a fuzzy cloud of electrons. Okay, so what happens in nonpolar molecules is we get this thing called an instantaneous or temporary dipole moment. If you think about it, if all my electrons are buzzing around and they were evenly distributed, but because they move randomly, at any one particular point in time, all my electrons might jump over to one side, which means this positive nucleus in here is now exposed. All this positive charge is exposed and all the negative charges over here. So realistically, we would have a dipole. Okay, we have a change in the distribution of the charge across the molecule. So the atom itself will become polarized for a very, very short period of time. But of course, our electrons are always bouncing around, so it won't take long and for them to bounce back over here. So these dipoles arise for very brief moments in time and then aren't there for very long at all. When they do arise though, okay, what happens is that they can induce this dipole moment in something else. Okay, so if we look at the hydrogen atoms in a molecule, at one instant, their electrons can be evenly distributed. At another, they might be all on the left-hand side, and then at another, they might be all on the right-hand side. Okay, so at these different moments, we would have a dipole present. Okay, so when we have those instantaneous temporary dipoles arise, what happens is we get our delta plus and our delta minus. These are now attracted to each other. But of course, as soon as our electrons jump away, that attraction goes away. So it's a very, very weak attraction that we see. Okay, depending on how many electrons we have and everything else, that will change the size. But if we get an induced dipole in, say, a Cl2 molecule, like this one here, as it gets close to another molecule, be slightly attracted to another molecule, it will induce that dipole in another molecule. If you think about it, the electrons are all over here, so they will actually repel other electrons, forcing the other electrons to move that way, and then this positive and negative will attract each other. Okay, so we can have an instantaneous dipole occur in one molecule, which then can induce a dipole in another molecule. Again, these are just temporary. They don't stick around for long. Okay, so when this happens, the overall substance will start to attract to itself, and we have what we call an intermolecular force. Okay, so the weak interactions from billions of temporary dipoles have a weak attractive force, and that is what we're talking about when we talk about London or dispersion forces. They are present in all molecules, okay? They are the only force in non-polar molecules. Okay, so they're present in all substances, but they're the only one present in non-polar ones. Okay, so London forces are also dispersion forces. They come about because of billions of instantaneous dipole moments, okay, and then they exist in all molecules. They are the only attractive force between atoms of noble gases or non-polar covalent elements. So now we know that how intermolecular forces in terms of dispersion forces arise, we need to look at what can influence the strength of them. Okay, so there are a number of different things that will influence the strength of the London forces that we see. One is the number of electrons. So if you can think about this, if we're getting these because all the electrons are moving sides in an atom, then the number of electrons we have will change the magnitude of the difference between the positive and the negative sides. So the more electrons we have, the stronger it will be. The other one is the size of the electron cloud. Again, this is related to how many electrons, but also how much space it's dispersed over. And then the third one is the shape of the molecules that are formed, so how close they can get to each other for those intermolecular forces to actually take place. So if we look at this now, if we look at the number of electrons, simply the more electrons present in a molecule, the larger the distance between valence electrons and the nucleus, okay? So the attraction of the valence electrons to the nucleus will be reduced, okay? And because they're not being held as tightly to the nucleus, it's easier for us to actually distort the electron cloud. So instantaneous dipoles are stronger if we have more electrons, and that means when we have stronger forces, we will have higher boiling points. And we can see that between neon, which has the atomic number of 10. So in a neutral atom, it will have 10 electrons, okay, and its boiling point is minus 246 degrees C, whereas something like krypton, which has 36 protons and in a neutral atom will have 36 electrons, that bigger electron cloud means that our dispersion forces are much stronger, and our melting point now, our boiling point is 153 degrees, so it's about 90 degrees higher than what that is for neon. Okay, so the size of the electron cloud, so this time what we're talking about is the volume and space over the total molecule. Okay, so again, we're talking about the ease of polarization within the electron cloud. So in the case of propane, which is this funny looking caterpillar guy here, we can see that we have C3H8, so we've got more atoms, so 3 atoms of carbon, 8 of hydrogen, and its boiling point is minus 42. If we increase the number of atoms now, so this of course will increase the number of electrons, but is related to the volume as well because we're increasing the number of atoms. We can now see when we go to C8H18, our boiling point actually goes up to 125 degrees C, which is actually higher than that of water. Okay, and that's because we now have this electron cloud distributed over the whole molecule. We've got more electrons and they're over a larger volume. We can polarize that cloud more easily. The more polarization we have, the stronger the attraction between the positive and the delta positive and delta negative sides of our molecules. Okay, and then of course the shape of the molecule, essentially the shape affects how closely molecules can stack together. If you think about if I have, say, pentane here, which is actually a 5-carbon chain, so 1, 2, 3, 4, 5. I'm not going to draw in all my hydrogens, but if I had another pentane chain, it could actually just stack in next to it so they can get nice and close together, so we can have limited distance between here so these chains can attract each other. If we go with 2,2-dimethyl propane, which will be 1, 2, 3, and then I have a carbon off here and a carbon off here, this guy can't stack as well now, okay? When we have two of these coming together, there's a bigger distance here, okay? So that greater distance means that they won't have as strong attraction to each other, and we see that the boiling point is actually much lower at 9.5, okay? Because our London dispersion forces are distance dependent, okay, it means that the further away they get, the weaker the force, okay? So if the molecules are branched, so they have a shape that won't allow them to stack, we'll see weaker dispersion forces. Okay, so I'm going to leave that here and stop this video. So get your head around that, and then we'll cover the next two types of intermolecular force, dipole-dipole and hydrogen bonding, in the next video, which has already been uploaded as well. Okay, so that's London forces. I'm actually going to stop this video here so you can digest that and then watch the next one on dipole-dipole and hydrogen bonding.